So this is about stack and context switching. Already we have gone through theory for this, but just a small recap on this. Okay, so now till now whatever we have done is like creating a task, introducing delay. Now whatever we have done is deleting a task, resuming, suspending, how to create different task, heap memory, all these things we discussed. Now comes two things. One is stack and the other is context switching. Theoretically, already we have done it. Now let's see what extra things we have in here. Now we know that task appears to run in parallel, but they are executing, it is executing only one at a time. It is single core, right? Just it appears to us that it is running in parallel, as there is only one CPU. If you have multi-core CPU, at that time also, depending on your course, only that many particular tasks will run simultaneously, not all the tasks, right? Now when we have a now we know that whenever a task A stops and task B returns, so what happens? CPU, how does this CPU particularly remembers where that task A was and from where it has to continue that, right? The already we have discussed this, that the answer will be like stack, right? So what does stack has? Stack will contain the task memory and the CPU context, right? So what is simple, in simple terms, what we have, stack will be is a memory area which we are using to store local function, local variables, return addresses and CPU registers during interrupts. Now the first point we made at starting, every task in RTOS has its own task. So here also it's the same thing. Every task has its own stack, right? Mm, Now, if two tasks shares one stack, then what will happen if we have two tasks sharing only one stack? They would overwrite each other, right? So we will have corrupted variables, some without knowing we may have crashes, and debugging will be very painful. Why? Because which task, as we are sharing that stack memory, which task is uh, making it crash, it is very difficult. It will be very difficult. So what will happen? Any RTOS you take, task will have their own stack memory and they are simply compared like functions, right? And if we have cortex m processors or cortex m controllers, so here the particular behavior will be like stack will go downwards, right? Which means that from high address to low address, that means if the memory is from 0 to FFH, then okay, so if the memory is from suppose uh, 00 to FFH, this is not memory. Why? Because this is very small thing which is simply like 255 bytes. I'm just saying that okay, your addresses in your memory location is like 0 to FFH. So if FFH is as FF is assigned, then the stack will have like FF is the high address and it will grow downwards. If this is the stack memory, if it is assigned, then the stacks grows downwards from high to low. That means it will grow like FF, FE, FD, FC, FE, FF, right? So high address stack grows down and it will go to low address. So how we are doing that? Already we know the operations we have, push and pop, which we use in stack, right? So with pushing, the stack pointer decreases, which means the stack is incrementing, right? And pop in the sense it is the stack pointer decreasing and increases, and the address again will go back, right? So here we have grow down in memory, push and pop instructions, and they matters in debugging. So so heap memory is assigned for task TCB plus stack for task A, TCB for task C, and TCB. So whenever a heap memory is allocated, it will be stack plus TCB will be there. Now we have the next concept is context switching. So what will happen in context switching is it will save the current CPU state and it will restore the another task CPU state. Already we have discussed this also, that CPU registers are saved on the task stack and then the it will be restored, right? So here you have CPU registers, program counters, stack pointers, all this has to be reserved. Okay, now suppose a task A is running and SysTick interrupt occurs. So what will happen now? CPU automatically pushes whatever registers are there in stack. Okay, and RTOS decides which task has to be executed next. So if when it decides what it will do, it will save the task A stack pointer into TCB, and task B stack pointer, it will restore from TCB. Okay, and it will restore the B registers also. So CPU resumes as if task B was always there running. Okay, so this is simply an illusion of multitasking. Now, if we have TCB, then uh, if we have TCB, what does this TCB contain? Each task will have a TCB, whatever it is. Okay, I think even in Linux for normal things also we will have TCB. If it is not RTOS, still Linux does have TCBs, right? So task a TCB will have stack pointer, priority of the task, state of the task, in which state it is, and list items. Okay, so stack pointer is in all of these, stack pointer is the most critical one. Okay, why? Because it will decide that what exactly uh, already we have faced some issues, right? If stack is too small, it will destroy our memory, right? And that is the reason this is very critical. So where this stack pointer will have in TCB. Okay, now if the stack is too small, what will happen, it will destroy, it will not work properly. So function calls, already we have seen the live example of printf, right? Printf or logging, it consumes lot and lot of memory, which simply crashes our system. Stack overflow will occur, and without any reason random crash will occur without any visible errors, right? Which we have seen already. So task switching will work because stack is preserved. Okay, and local variables will retain their values. So which means what, our whole program, if you consider 2-3 different tasks as different programs, so if the program is not completely executed, it has to reserve that uh, where it has stopped, right? Where the execution has stopped, as it is not completely executed. So that whole thing is done in TCB. So such that what will happen, as it reserves it, it will resume exactly where it has stopped. Now, without understanding this, we know that our system will crash. Now, so this is simply to create the task. Now, here, stack size, cortex. Okay. Okay. So here we have two defines for artist FreeRTOS config.h, which is minimal stack size. What should be the minimal stack size of each task? And config check for stack overflow. So check for stack overflow will have something like one more function will be there, which we will see. So check for stack overflow, we need to enable. Okay, so enables overflow detection. It will detect the overflow detection, and this one minimal stack size, if it is 128, whatever uh, tasks are created, the minimum stack size has to be at least that. If we have more, no problem, but at least it should be that much. Okay, so this is about the revision of stack. Now coming to some execution part. So here we have stack high watermark. Okay, now, so what is one of the biggest problems in RTOS? It is not something like speed of execution. The biggest problem is stack overflow only. Okay, so the challenge is like we don't know how much stack a task actually uses, right? So we need to guess, right? Guessing is dangerous. Why? Now, if I over allocate, it wastes my RAM. If I under allocate, the problems we have seen already, it causes random crash, right? Which that means what? We must measure our stack usage, right? Now, how do we size it correctly then? So we have one measuring tool, which is stack high watermark APIs. Okay, so high watermark, in simple words, it will say the minimum free stack that we have now. Okay, so here we have task get high watermark of handle. We need to pass the handle of the task. Okay, so it does not tell how the stack is used, or how much memory it has, like the detail. It will not tell us the stack, but it will say that how much we came near to overflow. Okay, it simply says about the minimum free stack we have now. Okay, so um, if we have a water tank, right? So here what will have, that's level of water will have, if we see the remaining part which is not filled, it is like the lower, it says that okay, here also it says that okay, this much amount of free stack is remain. Okay, it is not full, but it is this much stack is free. Okay, so basically this API is explaining how much amount of stack is free, unused stack to be precise. Lower value, which means it is closer to overflow, and if it is 0, then overflow has occurred already. Okay, so we need to find this value. One more thing we have here now. Okay, so this is the example code now which we are going to execute. Here we have a task, and we are saying we are taking one base type, which is uh, ubase type underscore t free words, and this is just a variable, and to this we are passing this high watermark. Okay, and then we will print this. Okay, one more important thing to discuss here is, you remember at starting when we were having a problem, we had something like a5 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 0x a5 was there, if you remember. Every time we were getting that only. So that is, just a second, Shravan. Sorry. So hope you remembered that pattern. We were getting A5, 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 A5. So when the stack is used, we get this that particular pattern, okay, which is overwritten. So this will allow that this will have this free RTOS to measure the usage. Okay, so if suppose we have return value, we will use this example. We will write whatever is there in our program. We will just add these two things and then we will see what exactly it is going to. So here it will return the value. Now if it returns 50, that means 50 into 4, 200 bytes of free memory is there. If it is 0, that means stack overflow already occurred. Okay, and always there should be some margin which should remain such that our program should not crash. Okay, so uh, here we have some sizing method. We have to allocate generous stack initially. Okay, and then we have to run the system with worst case. Okay, and then we will have to measure the high water mark and then add the safety margin. And if we have more amount of stack remained, then reduce the size of the stack. And if we have less amount of stack, then increase the size of the stack. But we should never guess it. So first to find out, run the worst case, check out the normal and idle. These peak usages will be high mark will capture. Okay, so to do this, here we have one setting, and that is hash include task get stack high watermark enabled. Okay, so if we are not enabling it, as we have already seen, API will not be compiled and we will not be able to measure this particular function. So where we are, what is the common mistakes we are doing here? We will measure it only once, right? Right. We should, we are measuring it in ideal conditions, but we have to measure it in actually worst case condition also. And here we should not ignore, we should not ignore even the ISR stack usage also. Why? Because there also we will face some issues. ये टूट क्यों बैठा नहीं आया? So let's create this one, and yeah, that is the. So let's check out in our program how we have this. Now we have this task one. We are simply printing it. That's all. So let's print this one. Only one is enough. Right. So we have created a task and we have task handle also. So we have task handle for task one. So we will check with task one. Task two, we have delay, delete. I'll just remove this all these things. Now, or else we will just remove task 2. We will just want to check out task 1. That's all, right? So let it be there in the function, but we will simply, I'm not changing any task name or anything. This is just like, if it is stack function, watermark function, I'm not enabling everything. So now I'm assuming that here my task needs something like 512. My stack depth is 512 bytes, right? Words, sorry. Now, uh, let's have. mm, so here, if we see, In this function itself, we'll copy this, we'll try to copy this, otherwise we'll have to write it. Oh, okay, let's see. Task 1. Yeah. So 3. So that's it, right? Here I'm writing null, which means itself, right? And we cannot use this segger okay, directly we are just writing this one, right? So have we need to print something else in this. So I'm copying this. So here I'll change it. Okay, so what I'm doing is like I'm just typing how much memory is remaining. So free stack is is equal to or colon whatever we want to write, and percentile new words. Okay. What just got disconnected? Okay, and then that's it. We need to have something else here. We need to pass few more things here, and that is free stack, comma, okay. So okay, I have written here word, so I'll just change it to free stack, or else here we need to change anything is okay. Our wish, free stack. Okay, that's all. Okay, and why we are displaying two? One is free stack, which is in words, and the other is in bytes. So here we are multiplying it into 4. Okay, so now if we want to print it, we are printing, and mm, that's all we have in this. Nothing else we need to print in this, right? Now let's build it. But we have not checked whether we have that particular function enabled. Where it is. Hmm. Let's just check it. If it is there, fine. If not, we will include it. I think it's not there. Let's include it. Okay. Hopefully this is the same function. See. Oh, already it's there. Hash include U task get. So we need not again, otherwise it will be right. Here it is enabled or not. I need to check. It's enabled, right? Now let's debug it. Run it. See here we can, as we are seeing using this RT printf, it is showing that this much amount of memory is remaining, right? As we are using this, we can see the output. 433 words, that means 1732 bytes are free. That means what? So in this particular case, as we have nothing, but we have included 512 bytes of memory, and that is the reason it's like wastage of memory, right? Even though we don't need it, we have assigned this much memory, right? So basically, it just use 512 minus 433. So the remaining amount of memory is used. Okay, so we have here one more thing to remember, that logging will affect stack. Okay, here we are simply printing, but if we are using logging, then at that time it increases stack usage. Right now we are just checking it, right? But if we have printing, stack usage increases the stack usage itself. Okay, and but as this is lighter than printf, we are not facing that issue as of now. And when we are performing worst case scenario, just now as we discussed, in that we need to include logging also, because we don't know, as right now initially if we are not using logging, that in then in future we may have this logging feature enabled in our particular application. Okay, and this particular API which we have used, right? This is a task get stack high watermark. This is to measure task stack only. Okay, it will not, if you want to measure something like ISR stack, then that is the different case. Okay, and mm, stack overflow in ISR, it will not show. Okay, now let's try if it is saying, we will just change the memory of this to 128. I mean the assigned heap memory to 128. So if we do that, 128, I think in minimum size is also 128 only here. Yeah, minimal stack size is 128. Let's see. So one not 49 words are left, right? So minimum size is this much. That's why we have, that means still we have some in something like margin is there, right? And till we reach this 49 to 0, it will be too late, right? If we got here 0, that means already it has overflowed and there is no safety margin left. So we have to be sure that we need to have this free stack. Okay, so how we need to do it like professionally, as we already discussed. First, allocate the stack, then run, then check for worst case, and then reduce carefully, right? And but we need to make sure that margin should be there. At least 30 to 40% should be free. Okay, why? It we may have logging or error handling or recursion, whatever it's going to come, but at least 30 to 40% has to be left. Okay, so this is about stack water high mark. Okay, now the next thing we have is stack overflow. One more thing here we have. Now suppose stack overflow occurred. What will happen? In our case, the previously we have faced hard fault, right? Hard fault was occurring. Now many sometimes people will check for error message. Okay, that okay, stack overflow happened and we can see error message for that. But in embedded systems, stack overflow will not create any sort of error. Okay, it simply cause memory corruption. Okay, now the CPU does not know what exactly the stack should be. Why? Why? Because stack is just a RAM and CPU only follows the stack pointer. That's all. It is not going to check for boundary checking or anything. So what will happen when the stack overflow happens? CPU happily keeps writing. That's all. Okay, and this will cause the problem. Now, so stack. mm each task will have, already we know, stack as well as TCB, and they are placed next to other objects in RAM, right? So what will happen now when stack overflow will occur? It is going to write in someone else memory also. Okay, so that is again very big problem. So, and the last thing we have is if stack overflow occurs. So what will happen? It may write to another stack's memory area. It may write in TCP fields, it may write in function pointers, it may write into variables, anything, right? And the worst thing is nothing will crash immediately, right? It will not happen at overflow time. When it will happen? It will happen when corrupted data we will use, right? When we are trying to use it, at that time crash will happen. So now, when the stack is stored, stack stores function return addresses, right? Now, if it gets corrupted, then what will happen? CPU will return invalid address, right? Address which is not executable, because the task which I am executing, it is trying to execute some other address. So CPU raises hard fault at that time. So in this way, it is going to go to it is going to create hard fault error. Okay. Hmm. And one more thing will happen if context is switching. The one which I said just now is function return address, right? Similarly, context switching will also restore stack pointer, right? So there also, if it corrupts the TCP, it is going to have invalid address. Stack pointer, if it has invalid address, definitely push and pop will have invalid access. At that time also hard fault will occur. And uh, if at all RTOS list pointers are corrupted, at that time access violation will happen and hard fault error, right? And the bugs which we have due to stack overflow are the worst bugs. Why? Why? Because fault appears without any reason, right? Because, and it is unrelated to the code, because our code looks good. There is no issue with our code, but we may have issue. We may get that error, and debugger may not show anything. Okay. So what we will try to see what is the problem with the compiler, or what is the problem with RTOS, or what exactly it is. But the problem will be stacked. Okay. So the best example we had is like creating the with less memory on the other board, right? We were calling printf. printf used large amount of stack growed, and we had hard fault, right? Mm, and here we have one more thing, but we will see that hook functions for that. Okay, so basically already we discussed all these things, so let's go to the next topic. So okay, so now this is the case study. Okay, so let's see the classic bug we have. System run for hours, suddenly hard fault occurs, and the fault location changes every time. If this is the problem, then it is a very big problem, right? Because the fault location is changing every time, it is very difficult to debug it, right? So here, if we see this one, so will we able to catch the overflow before it will destroy the system? Stack overflow detection is not perfect, right? But it is useful, right? So one of the ways, like FreeRTOS will have some particular values to detect overflow, like 0x A5, 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 A5 was the pattern, right? So stack will filled with that particular known pattern. The pattern is checked during the context switching. If pattern is corrupted, overflow is suspected. Okay. And the detection happens only when the scheduler runs. Okay. Now, so if you see this code, here we have taken how much memory array size of something 600, which is very large local buffer, right? And then we are using log to use that to print it, and then we are sending it through UART. And so this looks good, no issues, right? We have just allocated some array and we want to print it on in log, and we are sending the same thing whatever we are printing to UART also every 1 second. So this looks good, no problem. But why this will fail is the local buffer is allocated in the stack memory. Stack is also used by context switching, and ISR nesting increases this usage. Okay, so stack will simply overflow. So logger task runs normally, stack grows beyond limit, adjacent memory is corrupted, hard fault is occurs. So what are the debugging steps we have? First of all, stack overflow detection, config assert, break in overflow hook, identifying failing task, and measuring high watermark is one of the solution we have. Now, one is to increase the stack size. So previously, when it did, the memory which was allocated was less. Okay, here it's not there, but the memory was less, so increase the size of the memory. Increase the size of the stack. And the other one is move the buffer to the heap location. Okay, rather than in the current stack. So what will happen? Heap memory will be allocated. 600 bytes of memory will be allocated in heap memory and not in stack memory. So this will not cause hard fault error, right? And the other fix we have is we have to measure the stack high watermark, ensure margin exists, and make sure that it should run under worst case. So this was about one more thing. If we can have one more. So let's just check out if we can add something to it. So here, let's try something. So here we can have one hook function. Okay, hook functions are functions which are called by kernel itself. Okay, so now we are saying that first of all we will enable the check for stack overflow function here. So check for stack overflow config check should be there somewhere. Check for stack overflow. This is 2. Okay. Now 2 is like aggressive checking. If it is 0, then it will be disabled and 1 will be the basic checking. So it's better to have it 2 such that it will have good aggressive checking. Now what will happen now is whenever RTOS detects the overflow, it will cause this function to execute. Okay. So this function, let's write this function. Okay, so this function we will have, and this will be called by kernel RTOS. Okay, so let's write this function like the application stack overflow hook. Okay, so let's create this. Now inside the stack overflow hook, what we are going to do is Uh, so here we will simply use this RT only, RT logger, because but we can what we can do, we can turn on some LED, or we can have a buzzer sound, or we can just use this printf messages, or we can have error codes that if we print that error code, we can understand that okay, this has occurred, overflow has occurred. Okay, or we can have we can make it into an in enter into infinite loop, right? But we are not allocating memories. Okay, why we are not allocating memories? Why? Because already it is corrupted, right? Already the error has occurred, but we need to debug it. So suppose now the stack size is 128 bytes, right? Just now we did. Okay, I changed it. So again, I'll just make it 128 only. Now 128 bytes of memory is there. So here I'll add a array and logging. Okay. So what we will do is, mm, 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 mm. So here the code was there, right? Yeah. Mm. So I'm just taking any buffer and I want to print it. That's all. Because I cannot do other things here yet. So I'll just print it. So we are taking care some buffer size of some 500 will take. Why? Because anyway we have how much memory? 128 into 4, right? Let's see. We don't have much memory left, right? Why? Because we have only 49 words left, 49 into 4. So let's have 500, or we will increase it later. Okay, now we want to print this, right? So I'll just have this Segar RT again. I'll copy this. But why to copy this? I just want to check out this stack printf only, right? Now if I run it, let's see what will happen. I've just allocated some amount of memory, that's all. I didn't do anything else. I run it. For 68 bytes of memory. How come? 128 into 4. Okay, just make it 5000. See, hard fault occurred, right? Hard fault occurred. Why? Because we have allocated only 128 bytes of memory for that particular task, but we have used more than that. I have used some 5000 bytes only for in that local stack, and that's why. Now suppose if we don't have this particular mm, function like high water mark or something, then what will happen? Like now this is simply like it gives us an safe side, that's all. If the detection is disabled, then stack corrupts the memory, right? Hard fault occurred. We don't know where exactly the what is the crash location, and what debugging will be very painful, right? So this is one of the way we can just we have created a hard fault error, right? Now I'll just remove this also again. Now suppose I want to check it with this hook method. Just now we have written a hook function, right? Till now it just went to hard fault, right? Now I want to do it using this hook. Now what this will do is mm, it will enable the detection, right, and run the worst case scenario, right? So what I'll do is I'll just write this rt printf with the saying that system crashed, that's all. Let's see how it executes then. System crashed. Hard fault occurred. I have enabled it, right? This is okay. Mm, one second. Anything else to be done? Other things I have missed. Mm, one second. No, nothing is there here. So let's check out here only. Mm, 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 mm. Okay, so I think One more thing we need to do here actually, which I forgot, I think. Sorry, I did a big mistake actually. That is, here we need to pass the hook functions also, right? Why? Because when we said um we need to pass, when we have seen that uh, exam API, it mentioned there that we need to pass the hook function, right? Just a second. हेलो एक मिनट ओके ओके ठीक है ओके 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 Okay, sorry, I'm back. So, as I said, we need to pass a handle, right? So, I think we can just copy it from there, or else we need to write it down. No problem. Okay, I closed it. So, let's write it down. So, we have something like task handle. Here we have, right? Task handle. Hmm, yeah, task handle. So, here it can be anything. We will not have separate overflow hook functions, but task handle and something like some task, comma, and the other one was some name of function, I guess. Mm, Just a second. Overflow. Where it is? We have seen this, right? It should be here only. Mm. Function. Here it is. Okay, let it be. Let's write it down. Or else we can do nothing. Good. Trying to get an unadded document. Oh, we need to add it. Oh, okay. Let's see. The other one it was something like mostly it should be hand the task name only. Where is this one? Creation of task. Task create, go to definition. Why we are not able to? Okay. Okay, let's see if at all, if anything. Oh, here we have already. We task overflow with function. I have written it again. Oh, already it is there. So while of one, that's why it didn't executed ours. RTT also. So as soon as this occurs, one thing we need to do, and that is we should disable interrupts. Okay. So just to write task disable underscore interrupts. Right. That's all. Just to check whether this is the correct one or not. We are not going to, oh, I didn't stop this. That's why we are not able to go anywhere. Okay. Trying to get the ACT for non-documents. Okay. And after that, whatever we want to print, we can print in it. So I'll print just now what we have print RTT. No, scandal. I'll print the same RTT print where I'm saying that system crashed. Okay. System started was there. Let's print this. System crashed. That's all. We need not do anything else here. Let's see now. F7. Okay, I didn't do now. Security printf. What is the extra thing we need to add here? Secure printf. Why? Nothing is there. I need to simply disable this, and I'm adding only the while function. While of one. I didn't do anything here. Then why is this error? Let's see once again. Oh, it's done. No issues. Let's see again. We are having this issue. Run system startup. What happened? system is still running or what? Stack Overflow already we have checked. Idle hook. Tick hook is 0. This is 2. We should be able to see this name actually, that why. Mm-mm-mm. Mm-mm. What again is left? Oh, wait. Nothing is there now. System crashed. That's all. Let's pause it and see. Oh, okay. I'll just not disable the interrupts also. We will see why this is not working, but I want to just see. I'll just come and I'll have this breakpoint here. Let's check out. I don't. 10 minutes. Wait bit. Okay. Sorry for no, it is not coming here in loop function. Yeah, application stack. Okay. Okay. Let's see. J-Link error reported. Why? Once again, let's do it. If not, I'll just find it out what is the exact problem and we will see that again. No. Stack Overflow function, it's not coming to. It is going inside this only. Soft device present. We put suppress ticks and sleep. University would just block interrupts globally. Okay, it is this. Without this also, it is blocking interrupts only, but Segger, why it is not coming to the next one? Okay, I'll just check this out and then we will see. Okay, shall we continue, Shravan, or shall we stop?
Anything is fine, ma'am.
Anything is fine? Then we will continue. We will continue for next half an hour. But just to give you 5 minutes.
Yeah, you can debug.
Yeah, just.
I think it's not entering into that system crash loop also. It is
actually,
like
yeah. Even if
it's
it is
not entering here.
Yes, here it is not entering this particular hook function, but the thing is, at least
Hmm.
it should print.
Free stack.
Previously, it went to hard fault, right?
Yeah, yeah.
Hard fault it went to. Now we have changed that. It should not go to hard fault, but it should show us something. That is
It
hook
should
function.
print something.
Whatever we are
Yeah,
printing in, yeah, it should print. It should enter hook function first of all. It didn't enter. It is not entering into hook function at all. The other, there is no other configurations here actually. Hook function is enabled. Let's check out. 1 minute. It is enabled. Why? Because it's in our system already. I mean, a function is already there, so it should be there. Still, just make sure. Check for lock hook function. 1 minute. F hook. Hmm. Hey, no, 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 no. Ah, okay, just 5 minutes. I'll just come back.
yeah, yeah, sure. Yeah.
Yeah, just a small break actually. One- Thank you. Hi, Shravan, you're there?
Hello.
Yeah, yeah. Okay.
Yeah,
Hopefully, I'm sharing my screen, right?
yeah, it's visible. Yeah.
Okay. Let's just check out one more thing here. Hmm, So it is not entering. Let's try. Hmm, Without this, just now we entered hard fault, but with this, we didn't enter, right? So I have one doubt actually. Let's just check it out once. Hmm, What happened here? Right. Hmm, Task 1 500. It, hmm, we'll do one thing. In this, rather than this way, we'll just do like we are going to have some 50 bytes continuously, such that we can check the stack also, and if it will go to our uh, hook function or not, we can see. Okay, let's try this actually. And okay, let's see. That's will this work or not? Now we are increasing the stack memory. I mean, not stack. The memory we are assigning on each function. Nothing is working actually. What we did, it is not even executing task function also. Oh, I didn't disable this. Okay, see. Think we have printf task one. At least it should print our what is the size free task which is left. Nothing is working. It's directly going into ISR. Let's have more memory. Task one. Let's give 256 of memory. Build. Yes. Oh, here we mm, by mistake we did one. See, sorry, task one is not at all created actually. If you see here, it's not even showing error, but X task create is not there.
Yeah, it's commented. Yeah.
And that is the reason our nothing is working. Okay. I think while copying or something I did it. Right. Okay. Even it is not showing this mistake also. Fine.
Yeah. Yeah.
Actually, it should show. Why? Because we are passing parameters somewhere, but where? If we write simply without any data type, if we write, definitely we should get error. Okay. Now it started 165. It should allocate, right? Every time. So now char buffer of 50. We should allocate some memory. Okay. Hmm. It should do that. Do we? Hmm. Will do. Actually, one particular function is there. Let's check out whether this works or not here. The same API is there or not, I don't know. Some other name is there for recursive function. Some different APIs are there. So. But it should allocate every time 50 bytes of memory. Is it compiler is optimizing it? Uh, it's like a for loop then. I didn't wanted to write it. Let's write it. Event 1640 if it is defined here. Then t equal to 0. T less than, as it is char, I'm taking to 55 only. T plus, I'm just writing some values into this buffer. Okay. So buffer of t is equal to buffer of t equal to t I'm writing. Okay. That means it will simply take the values of 0 to 255. That means I'm writing something into my buffer. That's all. Okay. We have allocated this 50. Oh, here I have written 50 only. No? So I'll just make it, let's write 50 only actually. No problem. So 0 to 49, it will increment and it will write the same value to, if it is 0, buffer of 0 is 0, buffer of 1 is 1. That's all. बोल रही क्या बोल रही सुन बोल रही Still our buffer is not filling. Okay, so I think as this is like after this particular loop, that will be deleted, right? So that might be one of the reason, because every time we are calling now hard fault occurred. Okay. So one thing we can do is like we have to create one function and call that function recursively in task 1. Normal function we will create some void I'm naming it recursive only. I don't know here what exactly is the API for that recursive function. And here I'll just cut this thing and I'm calling this. Now, uh, now in this task only, I'll call this recursively. So first, and I equal to 0. Let's try this one. Directly, we will call this recursive function. Then recursive function should call itself again and again, right? Shall we write a for loop here? Or we can do one thing like we cannot create call the task of, we can do one thing right here in this only. I'll call my recursive function again. This is better rather than doing it in recursive function. So now this will allocate it continuously, and in this I'll call my recursive function.
That's better than for you. Yeah.
Yeah, recursive function. So once I call this recursive function, because directly using char is going into hard fault. If hard fault occurs, we cannot call our, it will not go into hook function. Stack overflow should happen, right? If it goes to hard fault, this will not execute. So our aim is to execute this overflow hook function, right? So we are building the overflow basically. So we are calling this recursive function, and now slowly it should allocate the memory continuously, and it should call this hook function again and again. So it's not going to come back here, right? We have not given any return. So it should not, and it should overflow. But one thing is there, will not be able to see this print that how much free stack is there. Okay, let's see. That also we will just check out. Let's see. No, hard fault only is occurring, which means it is allocating more amount of memory. How to allocate the memory in this such that it should build the what else we can do? One of the ways we can create the recursive function, and we should call this, but it should build up slowly. Actually, even doing this should build up slowly, but every time running a task is not. Yeah, we can do one more thing, and that is static char. Static will not delete the variables, right? It will retain the variables. Yeah, I hopefully at least this should work, but it should not go into hard fault. Hard fault only. Yeah, we will do this thing here also. Just an idea. Here also, it should not delete this, as this is static, right? It should not delete this buffer till the whole execution is happening, right? Right. But 177, it should decrease. No, it is not decreasing at all. That means only it is working. Till this function is executing. Okay. More thing. I'll just make it global. Acha. Oh, I I only did one mistake, which is like it is creating a buffer of 50, right? We are simply writing to that buffer only again and again. We are not creating new arrays. Only 50 bytes of characters we have allocated. That's all. Right. Right. So now what I want to do is I want to call this again and again such that our mm, memory should decrease. So now I have one more idea, and that is, let's see with this if it works well and good. For and in this I'm writing and I'm executing this one. If the memory is decreasing, then we will change the buffer size. Mm. Now I'm trying to create this 500 times. It should print and it should even say what. And I'm writing int such that it should have more memory. Let's see. No. Free task size is not at all decreasing. It's 177 only. Even if we do, how much is the memory allocated for this particular function? 256. Let's make it 128. It should not work actually now. It's only 178 is left. It should directly go to hard fault. 49. So I need to use more 49 bytes of memory into this. My memory should increment. How the stack increments now? Let's make it something like 1000. But allocating itself will, let's see. We are allocating it at a time and then we are. Why it is 49? Previously also it was 49. So even though we have increased the local variables, still it is showing 49 only. And that too int, not even char. Something is wrong in this. 49. It's stuck at 49 itself. Mm-hmm. To increase the stack here without calling recursive function. What else we can do? Such that mm, if this is decreasing 49 or not, I just want to check. Why? Because RTT will do that. Task 1 running 49 only. Why? Whatever we do, it is showing 49 only for 128 bytes. Somewhere else we have done some 128 bytes only. 128 words, sorry, 128 into 4. At least RTT should increase this. Uh, Allocating writing will not work. Why? Because allocating itself will cause crash. So other than recursive function, okay, let me look into it rather than wasting time that how to increase this uh, stack function slowly such that we should be able to see this. If I get the some idea now itself, we will do that. But one way I know is using recursive function. Okay. Just writing a recursive function, allocating a memory, again calling it continuously should work. But it is not executing here. It is not working here basically. If we call this recursive function, it's not working out. Anything, any other recursive function it should call? We can do recursive function. Wait. Two times if I call it, it should. $49. It got stuck at 49. Is it executing actually? It's working. Wait, parameter. Okay. No, it is working. Recursive is also working. But recursive has to be called inside a function. One way, I have one more way of doing it. Let's check that out. But okay, let's see once. One last thing, if it is not working, then we'll just leave this. Hmm. We will call it 50 times only. Basically, we are not calling this recursive function continuously, but we are calling it for 50 times. Let's see if this works. It came to recursive function. It went to hard fault. That means now also our uh, no 10 10, and here I'll make it because I just want to see the decreased memory. I want to show that. Okay. And here I'll change this to 256 or 512. Let's see 512 we will do. Now we should be able to see the stack size. Call it hard fault. Hmm. This is also calling our one running free task size. Okay. Mm. Okay, and let me check out this hook function. Why exactly it's not coming into this hook function? And we'll see. Okay. So next we have is queues. Okay. So now coming to queues here. So far now till now what we have done is each task was working alone, right? There is no dependency. But when we are working with different uh, real-time sensors or something, then we cannot work isolately, right? We need to share the data, right? So now if I want to send some sensors data to a particular task, how we are going to do? One few examples will be like just now we tried, like we can have a global variable, or we can have some flags, or we can have a shared memory also in between the task. Now generally we will do this in embedded systems, but in RTOS it is dangerous. Suppose now if two tasks are there and they are sharing same memory, then what will happen? Now task A writes to that shared memory data and task B reads that. And now in between this, context switch happens, right? So what will happen? Task B is reading which is not fully updated, data which is not fully updated, right? So here comes the race condition, right? Because both are trying to uh, write or read to that particular variable. So we have queues for that. So what queues will do? Queues will exist this race condition. Okay, so now these queues are used when one task produces data, another task consumes the data. Data must be transferred safely. As I said you, if one task which is producing the data got interrupted and the task switch happened. At that time, the another task will read the half processed data, right? So then we may have some consequences. So we have to make sure that the data must be transferred safely. So what does this queues do is this will copy the data. It will not share the memory. Okay. Now you can imagine a queue is a safe pipe between the task. It is simply uh, acting like a acting like a data pipe. Okay. So here comes the synchronization. Okay. Now in this queues, what it guarantees is no corruption of data, synchronization, task blocks it correctly, and ordering, which is FIFO by default. Okay, which is first in, first out. And here the logs are not needed. Okay, thank you. Logs are not needed. Okay, now let's create two tasks with uh, one is the producer and the other is consumer. Producer task in the sense it will generate some few numbers. Okay, and then it will send it to queue, and the consumer will receive that numbers and it will print them. Okay, and these tasks don't know exactly each other. Who knows it? Only queues know it. Okay, so what we need? We need like to create a queue we need two things. One is how many items and what is the size of each item. Now suppose we have some length of 5. Okay, so now that means if I have char of 5 at that time, 5 bytes. If it is int, then it should be the size of int, right? Now when the queue is empty, then and if the consumer tries to read it, then what will happen? Queue is empty, consumer will go into blocked state. No polling, no CPU waste time. It is simply st- uh, mm, what send it to. It will simply send it to the blocked state. And when the queue is full, and if the producer wants to write it, then it will have a pressure. Okay, so producer will be blocked automatically. So if the queue is empty, consumer is blocked, and if queue is full, producer is blocked. Okay, so with queues, there is no busy waiting. There is no manual locking like we have locking in mutex, right? So here there will be no locking, no race conditions, no CPU waste cycle. It will directly send it to blocked state. This is how the queues in RTOS works. Okay, so we have few APIs, which is like queue create. First, create the queue, which is of length. Just now we discussed. So here the length will be like 5, and what should be the size of it? Then XQ send and XQ receive, and pass the handle of it. So just now we discussed it will have FIFO ordering style, fixed style, and data is copied into the queue buffer. They are not shared variables. It will simply copy the data. Now, let's write this task. So we need a queue handle for it. And this is the producer task. We have some in a variable called 0, and we are incrementing it, and then we are sending it to queue. And the consumer task is like the consumer task. Simply it receives that, and we are going to print it using RTT. And in main function, we are creating these two tasks and data queue also. Okay, because we need to create the queue before receiving and sending data into it. So what will be the flow of the working is first create. Here create is not there. So first create the queue. Producer will produce the queue and it will send it using QSend. And the then it will be in queue buffer, and in receiving XQ receive, and the consumer task will use it or it will print it. Okay, already we discussed this producer consumer. So let's write a program. for this, and we need some settings. The is use queue sets and support dynamic allocation. Okay, so as why we need this is because queue needs dynamic allocation, and that's why we need this particular thing. Why? Because queues are the part of kernel. Okay, so we should have our output like received 1, 2, 3 in the task 2, which is receiving is our producer. Now, so let's just write this program and see how it is working. So this is basically data transfer, which is inter-task communication. Okay, the task is communicating with itself without global variables. They are using queues for it. I'll just copy these functions such that it will be easy. Mm, So let the functions be there, but we are not creating it. So even functions exist, no matter, no problem. So now this is my producer task. Okay. Oh, just not copying it properly. Okay. It's better to write it down rather than copying. Okay. So this is our producer task, which is a variable, and we are using this xq send. And what is it? The data queue, where we have the value. Okay, we are passing the address of this, and we are giving port max delay, which is defined here. It's not opening anything. There was a problem with the board. Okay, let's see. Okay, so we have this delay defined here, port max delay. You can check out port max delay. Port. Okay, I'll just check. Port max delay is somewhere like 100 will be there. Okay, so we are giving that. It's like a timeout. Okay, next we are giving some delay before sending the second value. This is simply a function where we are using this queue. The next we have is consumer task, which is going to use this values which we have just produced. So here is this one. This is my consumer task. In this, what we are doing is we are receiving what we have. From where we are receiving is from queue. So to receive from queue, we are using xq receive, and then we will give the same data queue, and we will have a particular delay, and then we will print that particular value. But here printf is used. We cannot use printf, so we will use this Segura RTT. Just copy this and paste it here. We have to receive received variable data. So I'll just write here received data. Received data is %ID, and What I want is only one thing, comma, hmm, received, right? That's it. This is our received function. I deleted all other closing braces also.
Yeah, curly braces. Yeah.
Yeah. Okay, I deleted it. Now the next thing we need to do is in main function, we need to create these two tasks and this data also. These three statements. It's like 256 KB of memory we are allocating, and we are not passing any handles. We are creating a size of 5, and the name of the data queue we have is data queue. Okay, let's introduce it here in our main function before starting the scheduler. Okay, that's all. Okay, that's it. Don't have anything else to do here. We are simply in place of global variable, we are using queues here. Now let's see how we are printing the output. So our output should be something like, already we have seen the received data has to start from 0, 1, 2, 3, 4, and so on. Hmm. Excuse, and I think use.h is not added in our main file. Yeah, use.h is not added. So let me do that also. This is only the q.c. Qs नहीं है, q है. So okay, ठीक है. Data queue undeclared first. Okay. Mm, so here we have created the function, and after that we are creating the task just to avoid this declaration. I have done it. Okay. Uh, uh, C, classic C programming error. If this doesn't work, then I'll have to do that declaration part also, because directly I have written only definition. Yeah. So, okay. Okay, we will have to do it in our way only. Mm-mm-mm. So anything did we miss? Nothing. So data queue, X create. That's all. Okay, let's see here then. Hmm. So data queue first used, but it's simply, I think, 1 minute. Just to go, if it allows, it is not even allowing actually. But let's go to q.c and check out. It is q.h only. I have done it. Main, it is same. The second thing we need to check out here is one more thing I wanted to check, and that is the type. Okay, so when we are creating this, so q underscore t should be the type, I guess, because here directly we have given only data queue. So let's see this one. This works. No, unknown type q underscore t. Why? We have included it in our main file. It is there. Mm-mm. Okay. So q dot h is the problem. Mm. Mm. Q underscore T. Isn't this the same? Unknown type it is showing, but here it is there, right? As it is not included in our files. Header file only is the thing. We have included q.h. Uh-uh. We have this. It's also same. Then okay, in this way we will try. In place of q underscore t, we will write handle. Maybe that should work. Mm, q handle underscore t. Mm, okay, gone. I can just undeclared. Data queue is already declared here. Wait, one more thing. Now, mm, now use data queue. Oh, it is. Spelling is correct only, right? Now I have declared it as name data queue. The name is different here. Okay. So basically, we have created it here and using it here. So what happened? It like it's not global variable, so it was causing problem. Like task handle, we have created now queue handle also as it's global. So in all functions also, it is not creating any issues now. Now just run it. Mm, data is 1, received 2, received 3, 4, 5. It's working. Okay. It's working properly. Let me do one thing. In this only, okay, this is just a queue. Okay. Is it clear? So it's working properly. Okay. So what we have done is we are using queues here to share the data between the two tasks. Okay. So here we are not using any global variables and we should not use the queues for large data. Why? Because queues copy data. And if we have larger data, then it will slow down the whole process, right? So in that case, we should use pointers. Okay. And We should not have even 0 block time. Why? Because it will waste CPU cycles. Okay. So basically, queues enable safe communication. It handles synchronization, task blocks automatically, and our order is also preserved. No race conditions. And it works properly between the shared data. Now, suppose in place of this, right? Now, this is the value is there. Now, if we just make it, now I don't want to share the data. Okay. And I want to increment the value of it. What will happen? I don't have anything else. I just have mm, and received. We don't even have received. So now I just want to do one thing. I just want to make this a global variable. Okay. And I want to increment this value here also. And I want to print this value here. And at the same time, I want to increment the value here also. Value plus plus. Okay. And I will print that incremented value from now. We are having only one variable, which is global variable, and we are incrementing it in both functions. And I want to print this. So how it will print? Now, value. Yes. So I'll write task 1. Task 1 data is this one. And I'm writing here value only. Why? Because this is our variable. And the same thing I want to do it here also. Now, these should race each other, that which task is going to increment it first. I didn't write backslash or backslash n, I think. Backslash or backslash. Do it again. Now, see this data. And this is from task 1 only, right? So, task 1, task 2. Okay. 1 minute. I think in this I didn't change this task 1. So, I need to change this to task 2. Do it again. And introduce some delay. Like here it is 1000. Here there is no delay. So let's have delay also as same. And the priority is also same. I'm removing this and introducing delay. Task 1 data is 1. Task 2 value of task 2 data is also 1. Okay. If you see here, what should happen? It is not doing it properly, right? Here, value of task 1 is, task 1 data is 2. And after that, value of task 2 data, backslash. Okay. Now just check this out. Here, is this the correct increment? No, right? Why? Because this is a global variable. This is not declared inside a function. Did I do that? One way at one place, did I make it? Let's just to check that also. This is a global variable only. Int value. Ah, I did. Now it should do it perfectly. I'm doing so many mistakes. The weekend mistakes. So as of now, it is working perfectly, right? One is 13, 14, 15, 16. Now suppose if I say, sometimes it may happen that it may not be able to do it properly. At that time, one will increment and the other will block. Or if I just remove this, now what will happen? Now if you see, now it will be a problem. Which task is going to, it came into hook function now. Nice. No, it didn't came. I'll just pause it. And if you see, actually what should happen, how it is going to see that what exact data is there and which is incrementing. The value of this data is incremented by task 1 only till this, and then when the context switch happened, after that task 2 got incremented, right? So now if at all in between, if we just read the data at that time, we may have corrupted data. Okay, so it will create a race condition there. To avoid that, we have to use that data very properly, and that's why we go for queues. Okay. I hope the basic of this queue is understood.
Yes, ma'am. Yes.
Yeah. So now we have one more function API for this queue, which is queue send versus queue override. Now in this, what we have is so yeah. So some applications, some applications will care only about the recent data, right? I don't want the past data. Like the latest sensor readings or latest UI updates. I want the latest one. I don't want what was there like 5 minutes ago on the UI, right? I want to see only the latest update. So previously what we did, we used only QSent data. Now, suppose there is a condition where the producer is faster, but consumer is slower. So at that time, I will have more data to be, I have more generated data, but I don't have that fast consumer. Now, suppose this is the there. Value is incrementing very fast, but the consumer can handle only um, like UI. It is slower. In this case, if I see here, uh, right. So till now we did this, right? Now we had this delay function also here, na? Okay. right? This was our function. Now suppose I am introducing delay here also. Till now this was working perfectly, right? It was producing and this was printing. Now suppose I have here 1000, but here I have only 100. Okay. Now my, if I want to print this, I can print this also. So I'll just take this and I'll print my value plus plus value. So produced data I'll write here. Produced data is value, right? So basically what I'm doing here is I'm printing my value, but I'm reading after 1 second. Okay. Now it should not receive all the values, right? Or is it slow? Let's see this. And I'll just receive the print and I'll have this value. So now we have here reset again. Just now what I said, I'm producing that, okay? So right now, if you see, the produced data is 2, right? But received data is 1. Then produced data is 3, 4, 5, 6, 7. Now if you see the next one, the received data is at 2 only. That means I am producing it continuously, but I am receiving it. I am receiving the old data, right? I
Yeah,
have
the old
produced
items.
till 8, but
Particularly.
I have received only the second data. That means my data is very old. So if this is the case in UI will have so many bugs in it, because right now I need the present things. I don't want the old things, right? So here what is there? The producer is faster than the consumer. Now eventually what will happen? The queue will become full. Okay, queue will become full before all the data from the queue is consumed, right? So now we will have backlog. Okay, our message, each message which is generated is important, right? And only the latest data matters to us. Okay, so here we need to preserve all the data such that we do not lose any data. If queue had space, then what we have done, item will be copied. Now if the queue is full, then task will be blocked, right? Or it will fail. It will check for that particular timeout and it will fail. So queue will act like FIFO. First which entered has to be thrown out, right? First in, first out. That means till the producer utilizes all the, or consumes all the data, the queue will wait, right? Now this blocking behavior here is intentional. So producers will slow down, consumer will catch up, and system will be balanced, right? Now, but with this, we have generated so much of data. But if we are not interested in the historical values and we are interested only the recent data, then we have one more API, that is queue overwrite. Till now we used queue send. Now I want queue overwrite. I care only about the latest value. I am not concerned about the historical value. So I want to just overwrite it. Okay. Now if I just remove this, at one point, what will happen? We will see where the queue should become full. Produced data is 12, 13, 14. How much? What is the size? Size of int, right? So let it till then we will just see this. Okay. So we have overwrite. Now here, what will be the difference is queue send, what it will do, either it will fail or block if the queue is full. But what queue overwrite will do is always it will succeed. And the old data which is already present will be discarded. But here the condition is the queue length must be 1 only. There our queue length was 5, right? We can define our own length in queue send. But here the length is 1 only. If queue empty, write. If it is full, overwrite. Okay. Previously, it was if queue was empty, it was going into block state. But as we have the length is only 1, if it is empty, write into the queue. If it is not empty, overwrite it. Then the producer will never block and old data will be thrown away. X overwrite is valid only for the length of 1. That has to be kept in mind. This is very important. And one of the key difference between XQ and XQ overwrite. Okay, overwrite, when it will make sense? When only particular slots are available, right? And for longer queue, it will become very ambiguous, right? Why? Because we have so much amount of data there, which to overwrite and which not to, it will become very complicated. So we have only length of 1 only. Now, if we have two, again, the same producer and consumer task, one is one producer and the other is consumer. Okay. So here, this is the producer task. So what we are doing is sensor. We are reading a particular sensor. Right now, we don't have a sensor, so we will have to read the value only. And then we are overwriting this value into the, we are sending it. Okay. Now, in consumer, what we are doing is we are reading the same one, which is queue receive only. Only queue send is changed with queue overwrite. Rest of it, it is same. And here, xq create has to be 1, which is size of integer. That's all. Okay, so previously we have, here it's still running. Yeah, it's still running. So previously we had the queue create of 5. Length is 5, right? Now the length has to be 1 only. Same task, only different APIs. Okay. Now you have seen the received data and if you see the produced data was more and received data was running behind it. Now what will happen, we will see. So how our output should be. Now I'll just stop it and I'll change this to overwrite. Now I have only 1 and in this consumer, the produced value is this and here I need to change it to overwrite, right? Only that is the difference. So if I can copy this overwrite, XQ receive, XQ overwrite. Okay, 2 queues are there and I'll remove it. So here I have queue overwrite. In place of that, I'm writing data queue and the value of it and the port max delay. That's all. Okay, whether it takes two values or it will not open. I have to get no, I know why it is. Okay, so here the only difference we had is like x over, in place of send we are using overwrite. Okay, so what should be the expected output here? Now if you see the expected, how it will work. So queue length is 1 only. So first it will produce the data, queue will overwrite, queue will hold the latest value and it will receive. Okay, now even though the data is there, so here I have 1000 ticks, here I have only 100, right? That means my producer is faster than consumer, but my consumer should be updated. That means at that point of time, whatever value it is producing, I'll display only that value, received data. Previously, what was happening? If it was 8, then also it was displaying 1 only. Received data is 1, then received data is 2. So our data was saved. Now our data will not be saved. I am just worried only about my latest out data. So here, okay, support max delay is not. Okay, let's see now. Backslash n is there. Okay, so if you see here, if you observe here, the data produced is 1, received is 1. After that, it produced 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so when the produced data is 10, at that time, my received data is also 10 only. That means I am receiving only the updated values, right? All these values are overwritten, right? So in this way, our queue function, this is one of the inter-task communication. Okay, so in this way, we are changing the data between using queues, and when we should not use this overwrite is when we are doing logging part. Okay, why we should not use it during logging part? Why? Because why we do logging is to have whole proper what exactly is happening, right? We don't want only latest values in logging. We need all the values. Okay, and then we in communication protocols or command queues, we don't want to skip anything. We should not overwrite it. Why? Wherever there it is not acceptable for loss of data, we are not supposed to use overwrite. In the places like sensor values or in UI, it is useful. So display always shows latest sensor values. Intermediate values are discarded and no blocking on full queues. So no blocking will be there here. This is about length, what it is, XQ and XQ overwrite. Okay, so when history matters, XQ send. When freshness matters, XQ overwrite. Okay, and already I said we should not have very big amount of logging things when we want to do override. Okay, we should not use it. So basically in real time functions, we can use it for UART command parser, or in event logging, queue send is used. Queue override, already I said you, wherever GI is there, refresh data is there, we should go for XQ write, sensor sampling, telemetry, all these things will have XQ override. Okay, I have one now. All the topics are very much important, but we will continue tomorrow. Till now, we had only one producer and one consumer, right? Now we have multi producers. Okay, so all are producing task and single consumer. So we will see this also. Okay, then we have queues from ISR, binary semaphores, counting semaphores, mutex, priority inversions, but we will see that tomorrow, not coming in that particular.
That recursive function thing, yeah.
Yeah, other than that, anything related to queues?
Queues are understood properly.
Stacks?
Stacks also, yeah.
Stacks, only this, other than this stack overflow hoop function, whatever we did, it was clear, right?
Yes, ma'am, yeah.
So we will see that tomorrow then.